Okay, today we're going to talk about the thermodynamics of solutions and then leading up to binary phase diagrams. You've already had a lab on that, so you know all about it, and I'll just refresh your memory a little bit. Going back to the general conditions of equilibrium, I've said this a number of times, but let me repeat it again because it is so central to understanding what happens in materials. We look for a thermodynamic potential, which will tell us what equilibrium states of the material will have and in what the thermodynamic driving force toward equilibrium will be. What that thermodynamic potential is depends on the experimental variables we have under our control. For an isolated system, we control the content, energy, volume, chemical composition. The thermodynamic principle is that the entropy must be a maximum for given values of those variables. Thermal contact, we control temperature, volume, and chemical content. The governing thermodynamic potential is the Helmholtz free energy, which must be a minimum. Controlling temperature, pressure, and chemical content, the governing thermodynamic potential is the Gibbs free energy, which must have a minimum value for the given values of Tp and N. And finally, in an open system, just a box that we draw in space, it's the work function, omega of Tv and mu, chemical potentials, which is just minus Pv, that must be a minimum, or equivalently, the pressure must have the largest value it can have for the given values of T and mu. Can we evaluate these quantities? Well, for a simple solid, the Helmholtz and Gibbs free energies are essentially equal because this Pv term is negligible. In that situation, we can evaluate the Helmholtz free energy more easily. And the Helmholtz free energy of a one-component system is just given by this little formula down here that we derived before. The only quantities that it contains are the energy of the material of the system at the zero of temperature, which is a function of volume only. And these days, you can crank and grind in a computer and actually calculate this for a solid of known configuration. And the other parameter is the specific heat. We discussed the sources of the specific heat last time, finished up last time. The specific heat of virtually all solids of interest to us is dominated by the vibrational contribution to the specific heat. And that has kind of a universal function. It goes like T cubed at low temperature and then asymptotes to a high temperature limit at a material parameter that's known as the Debye temperature. What the Debye temperature is, qualitatively, is just a temperature above which you can assume that all the vibrations are as activated as they can be. So if we know the Debye temperature, we have a pretty good idea of what the specific heat is, we can then calculate the Helmholtz free energy. The consequence of the Helmholtz free energy, where we particularly apply it, or Gibbs free energy, whichever one you're going to use, is that if we know that as a function of temperature, then we can determine what phase or what structure will be preferred at a given value of the temperature, because that phase or structure will be whichever one has the lowest free energy. Since the free energy is E minus Ts, at absolute zero temperature, the preferred phase will be the phase that has the lowest energy. As we come up in temperature, however, a high energy phase may have a higher value of the entropy, which means that its free energy will drop more quickly than that of the low energy phase. And as a consequence, we may have a change in phase, a change in the preferred structure or the preferred state of aggregation at some temperature, and that gives us a system that has one phase at low temperature and another phase at high temperature. In the case in which we're talking about a solid, a liquid, and a vapor, you know all about that. Solid at low temperature, generally liquid at intermediate temperature, vapor at high temperature. The energy of the solid is usually less than that of the liquid, which is less than that of the vapor. But the entropy of the vapor is greater than that of the liquid, and it's greater than that of the solid. So as a consequence, you have that progression of phases. We also have in many materials a change in crystal structure for precisely the same reason. At the lowest temperatures, the minimum energy crystal structure will be observed, but as we go up in temperature, there may be other crystal structures that have higher energies but higher entropies as well. So the free energy curve drops down, cuts through this, and we get a transformation structure. And that's common in many, many important engineering materials. In general, if we're talking about two phases, like two crystal structures, we can kind of quickly say which one will be the low temperature phase and which the high temperature phase. If a phase is going to appear at high temperature, if it's going to supplant a phase which has minimum energy at low temperature, then one quick thing that we know about that phase is it will have a lower Debye temperature. If a phase has a lower Debye temperature, then its specific heat will be higher through this whole temperature range leading up to the Debye temperature. That gives it a higher thermal entropy, and as a consequence may cause it to appear. Now let's go to the next stage of sophistication, which is as sophisticated as we're going to get in this course, in which we allow the possibility of a solid solution. We have more than one component. Now, if we have more than one component, and the two components organize themselves in a perfectly ordered crystal structure, then the thermodynamics we've been talking about applies. Because there's only one state, there's no configurational entropy. All we have to worry about is the energy and the vibrational entropy, and that follows pretty much the same rule. An ordered compound has a Debye temperature just like an elemental solid does. So there's really no difference, as far as our thermodynamics is concerned, as far as our discussion is concerned, between one component solids and two three-component solids so long as they're perfectly ordered. But now let's consider the possibility that we have a solution. Instead of having a perfectly ordered configuration of atoms, we have the atoms distributed over the sides of a crystal lattice in some more or less random way. If that happens, then there is a contribution to the entropy out here. By the way, there's an error in this formula, as I showed in the last set of notes. There's a contribution to the entropy that comes from what we call the configurational entropy, and that just adds to our free energy. That configurational entropy turns out to be enormously important. It has, for example, as I'll show you in just a few minutes, the consequence that there is absolutely no such thing in the whole wide world as insolubility. You may have been taught in your chemistry course at one point or another that this oil is insoluble in water. Not true. Everything is at least a little bit soluble in everything else. And the reason is because of this configurational entropy, which is always drives to cause two components to mix together and form a solution. So let's see why it is and why that's true. The way configural entropy comes, remember that one way we can understand and calculate the entropy is from the degeneracy. The entropy is associated with the logarithm of the number of distinguishable states that a system can have. So let's consider a system that has n atoms, n atom positions, and those n atom positions are occupied by n A atoms of type A and n B atoms of type B, whatever they may be. The number of, if we randomly distribute these, the number of configurations that we can have. Well, if I take the first position inside the crystal, there are obviously n factorial different ways of doing that. I can choose the atom in the first position in n ways, the atom in the second position in n minus 1 ways, the atom in the third position in n minus 2 ways, and so on. So there are n factorial different ways that I can arrange atoms over n atom sites. But not all of these ways are distinguishable. If the A atoms are indistinguishable, then interchanging two A atoms in some configuration wouldn't change the state at all. So I've got to recognize that of these n factorial possible configurations, n A factorial of them just come from redistributing the A atoms, so they're identical. N B factorial of them come from just redistributing the B atoms, so they're identical. So the total number of distinguishable states is n factorial over n A factorial times n B factorial. Yeah. If you're talking about, in fact, I'll get to that in just a few minutes as an example. If you're considering vacant sites on a crystal lattice, the vacant sites are a component. For example, one possibility for A and B would be A is copper and B is vacancies, okay? So it's the same thing. And I'd like to use that in a moment to compute for you the equilibrium concentration of vacancies in a solid. There is, to get this quantity solved in some useful form, there is something in mathematics called Stirling's approximation. It's remarkably accurate, actually, even when n is a relatively small number, like 5 or 6. And it says that the logarithm of n factorial is equal to n log n minus n. So let me just plug that in, and I get that the configurational entropy is k, n log n minus na log na minus nb log nb. Now, if I let x be the mole fraction of the A atoms, Na over n, then I can quickly just divide through by n, and I get the configurational entropy is minus nk, x log x plus 1 minus x log 1 minus x. And this is the configurational entropy of a random solution, a random distribution of atoms over lattice sites. Well, in fact, if you make a solid solution, you will, at reasonable concentration, you won't really have a random distribution of atoms. The reason is that the A atoms will either like other A atoms or they'll prefer B atoms, so there will be a tendency for the atoms to cluster, and the entropy will not be precisely equal to the value you get from a random solid solution. But it's not that far off in general. Moreover, we can show that when one of these numbers is much bigger than the other, we have a dilute solution. In the limit of dilute solution, in the limit that x becomes small, the random solution configurational thermodynamics becomes exactly correct. So this expression is strictly correct when x is a small number, and is still not that far off. We can at least use it for our understanding when x becomes a significant number. So this is the configurational entropy that we can calculate, and it's straightforward, and this is what it is. Now let me solve a couple of problems with it. I want to use it to show you two things. The first is the equilibrium concentration of vacancies in a solid, and the second is the proof that everything is soluble in everything else, which originally comes from Gibbs. Suppose that we have a concentration of vacancies that's x of v. So we have a one-component solid, keep life simple, and it's got some vacancies in it. Suppose that the energy of a vacancy is just E sub v. We want to find the configurational entropy and then use that to calculate the equilibrium number of vacancies. Well, the number of vacancies is always going to be pretty small, as I'll show you in just a minute. So I can assume the configurational entropy that we just found, and here's the configurational entropy. Now let me just plug in. If I put in a number of vacancies, or a fraction of vacancies equal to xv, the energy increase, if each vacancy has energy EV, the energy increase is just going to be n times xv, which is just the number of vacancies, times EV plus kT configurational entropy. And that's the increase in the free energy. Now, the interesting thing about vacancies is that they can be created or destroyed. I don't have a fixed number of vacancies, because lattice sites can become vacant by adding vacancies from the environment or by climbing dislocations. So the number of vacancies is going, remember that the Helmholtz free energy has to be a minimum. So what's going to happen in a real solid, what does happen, is that the number of vacancies adjusts itself by these various mechanisms so that we wind up with the minimum value of the Helmholtz free energy. So what is that minimum value? Well, I just take this expression for the free energy of a system that has this many vacancies, the increase in free energy. I differentiate it with respect to xv, and I set the result equal to 0. When I differentiate with respect to xv, I get this right here, this term right here, as you can see just by differentiating. And when I set that equal to 0, I wind up with the expression that kT log of xv is equal to the energy of a vacancy, or the fraction of vacancies is the exponent of minus the energy of a vacancy divided by kT. Note that vacancies are high energy defects. So if we go all the way down to absolute 0, what's the concentration of vacancy? It's going to be 0. It's going to be 0 because at absolute 0, it's the minimum energy that we're looking for. And right here, let t go to 0. This is exponent minus infinity, which is 0. So we get the right answer there. Vacancies appear because of configurational entropy. If there was no configurational entropy, we would never get a vacancy. They increase the energy, but because of the configurational entropy, vacancies appear, and here's their average fraction. I'm assuming the vacancies don't affect the vibrational entropy, and to a pretty good approximation, they don't. So how many vacancies do we get? A not unreasonable value for the energy of a vacancy in a typical, let's say, metal crystal is about 1 electron volt. In fact, you're not that far off if you assign 1 electron volt to the energy of a vacancy in anything. It's always going to be of that order. So let's let it be 1 electron volt, and let's plot the constant or the logarithm of the concentration of vacancies as a function of the absolute temperature. We get a curve that looks something like this. That's just the usual exponential curve. And to give you some numbers, at 300 K, room temperature basically, the fraction of vacancies is 10 to the minus 14th. I'm not quite sure what 10 to the minus 14th is. 1 billionth would be 10 to the minus 9. Anyway, it's a very small number. That tells you that at room temperature, in a typical solid, you have a vanishingly small concentration of vacancies. That has a big consequence. Because as we discussed way back when we talked about vacancies, one of the main things these vacancies do is that they allow atoms to move through the solid by exchanging with the vacancies. Well, if I've only got one vacant site in every 10 to the 14th, I'm not going to see much motion because the atoms aren't going to be able to find vacancies to exchange with. The net result is, and we'll see this again later, down around room temperature, solid state diffusion of substitutional species is just about dead zero. It just doesn't happen. And that's why you just don't have any vacancies. Unless you happen to have a crystal structure that's much more open, like a silver chloride or something of the sort. Ordinarily, no vacancies, no diffusion. Get it to around 700 K, however, and all of a sudden you've got a part per million of vacancies. Well, that's still pretty small, but it's big enough to have an effect, as we'll see later on. Not very much diffusion, but at least some. You get up to 1100 Kelvin, and all of a sudden you're 10 to the minus 4 vacancies. 1 in every 10,000 sites is vacant. Well, what that will tell you is that roughly 1 in the, 10,000 is about, 30, it's about 30, what's the cube root of 10,000? About 30, right? Is that, however many. So that says about, the distance between vacant sites is about 30, and interatomic spacings. And that's enough that all of a sudden you can get a rather significant amount of substitutional diffusion. And you get the temperature even higher, the number of vacancies keeps dropping down, and the motion, the redistribution of species becomes much easier. What does that say? If you're going to move substitutional species around, you got to have a good furnace. You got to get up to good high temperature. And the reason is not really the mobility of the atoms. They're a little bit more mobile, but not a lot. The reason is the equilibrium fraction of vacancies. If I'm going to cause atoms to move for substitutional, I've got to provide vacancies for them to exchange with. And the easiest way to do that is just heat the thing up. There's some other ways too, which we'll talk about later. Second, everything is at least a little bit soluble in everything else. Okay, the solid wants to minimize its Gibbs free energy. So if I take two pure components and bring them together, if they can lower their free energy by one dissolving in the other, they will. So let's look at this. Let's take the Gibbs free energy per atom. That's just G prime of X, which includes everything but the configurational entropy. Here's the configurational entropy. And since I'm interested in that first little bit of solubility, I can assume that the random configurational entropy is accurate, as it will be. So let's see how the Gibbs free energy changes if I change the mole fraction of a solute, and then I'm going to take that all the way to 0. Well, the partial g with respect to x turns out to be just the difference in chemical potentials between the two species. That's dg prime with respect to x here, plus kt log x over 1 minus x, where this is the concentration of the solute. Now let's take it to 0. There is no reason to believe, in fact, every thermodynamic model in the whole wide world will tell you that this term is perfectly well behaved as x goes to 0. So we can ignore this. However, look at this term. You know what the logarithm of 0 is? The logarithm of 0 is negative infinity. And that's telling you that the very first little tiny bit of solute you add to the solution is going to drive the free energy negative, and it's going to do it in a really big way. So if I have two pure components, one of them has x equals 0, there is eventually an infinite driving force to get that first atom into the solute. This is something that Willard Gibbs was the first to point out, and it means that everything is at least a little bit soluble in everything else. That has a whole bunch of implications, some of which is kind of funny. For example, take a cubic centimeter of just any material. You can assume with considerable accuracy, 10 to the 23rd atoms in a cubic centimeter roughly, 10 to the 22nd, something of that order. You can assume with pretty reasonable accuracy that the entire periodic table is present in that tiny little piece of material you're holding. Every single atom there is there, because 1 in 10 to the 22nd is a very, very small number. It also gets into some bizarre things. I remember a couple of years ago I was asked to write a letter to the governor. And the reason was that, actually they kind of got around that this year, I don't have the final law word, but the legislature had passed a law that was concerned about the damage to bird, wildlife, condors in particular, by lead and ammunition that was used in hunting. Hunters would shoot ducks, let's say. If they didn't retrieve the duck, the condor would show up and eat the duck and get the lead ammunition, and this was causing problems with condors. So they passed a law that said, we're going to outlaw lead and ammunition. Well, the law went filtering up toward the governor's desk, and some people who opposed this law came in and said, this is idiocy. You can't outlaw lead and ammunition because it's impossible to create ammunition that has no lead in it. So they came to me and they said, would you please write the governor a letter talking about what this happens? Well, we talk about, for example, there's a whole group that I get involved in. It's the lead-free solder group, which has to do with lead-free solders and microelectronic devices. Well, we, of course, never pretend that those solders are really lead-free. Of course they aren't. When you say lead-free, what you do is you put down a number, maybe a 10th of an atomic percent, 100th of a part per million, something. You put down a number, and you say, we're going to require that the concentration of lead be below this number, and when it is, we're going to use the term lead-free to describe it. But it isn't. It never is. And so I wrote a letter to the governor explaining this. He finally vetoed the bill on the grounds that even though this is what we mean when we say lead-free, that wasn't what the law said. The law said no lead, and that's absolutely impossible. Therefore, the second law of thermodynamics makes this law invalid. They passed the lead-free law this year. I haven't read it, so I don't know how they got around that problem. Presumably, they incorporated some reasonable standard of what they mean by lead-free, and then you could pass a law that would make sense. But everything is at least a little bit soluble in everything else. So if someone comes up to you and they say, this is insoluble in that, they are telling you a falsehood, unless they have put asterisks on that statement. And we're going to qualify with a statement of what they mean by insoluble. Okay, that gets us to equilibrium phase diagrams. Changing T theory X may change the phase of solid. The phase is state of aggregation, gas, liquid, or solid, or a particular crystal structure. We would like to know, and in fact you did this in the laboratory, we would like a simple way of understanding, because it's very important in material processing in particular. If we take something that has a particular composition, and we give it a certain temperature and pressure, generally we're talking atmospheric pressure, so temperature is the only thing that really matters. Suppose we have a certain composition and a certain temperature. We would like to know, if we let it come to equilibrium, what phases will be present. What crystal structure will it have, or mixture of crystal structures? Will it be solid, liquid, or a mixture of the two, or what will it be? And we represent that information in phase diagrams. Phase diagrams are nothing more than maps. We'll assume atmospheric pressure, maps that show equilibrium phases as a function of temperature and composition. We'll consider equilibrium phases in one component systems, which is trivial. We've effectively already done that. Two component systems, which is, has the configurational entropy and therefore the richness of phase diagrams. When you get to three component systems, like it's kind of tough because it's harder to represent the phase diagram. In fact, one of the great challenges in material science has been to, if we get to systems that have 3 and 4 and 5 components, as most commercial alloys do, how do we go about representing the phase diagram? Because we would need a 4 or 5 or 6 dimensional figure in order to do that, and most of us have considerable difficulty drawing 4 or 5 or 6 dimensional figures. So it's always a challenge as to how you go about representing a phase diagram for a complicated system. But for two component systems, you can represent the phase diagram very simply in 2 dimensions. 3 components, you need a 3-dimensional phase diagram. I'm not going to do that in this course, but it can be done, and you can see them, you can visualize them. Once you get beyond 3 components, visualizing the phase diagram is kind of tough, but it still exists. Computers don't have any problem at all working in 6 or 7 or 8 dimensions. So you can ask the computer, here's my temperature and composition, what are my phases, and it can spat out an answer. You have no problem. But drawing them is hard. So we're going to focus on 2 component systems. If you understand phase diagrams with 2 components, it's just not that hard to leap to more complicated systems. 1 component phases are very easy. Ordinarily, the phases that we talk about are discrete. That is, they're distinguishable from one another by their symmetry, by characteristics. So let us say you give me a system that's an alpha or beta or gamma, whatever these phases are. Such materials that have discrete changes when they transform into one another give rise to what we call first-order phase transformations with discontinuities in certain of the thermodynamic properties. The phase diagrams that result from that are something like this. Suppose I have alpha, beta, and gamma. Beta is the preferred phase at low temperature because it has the lowest energy. However, as we come up in temperature,